Digital. What is a digital sensor? So in the end, a sensor is of course measuring its environment, but the representation of that data is by a digital sensor protocol. I named a few here. Some of you might be aware about these abbreviations, but these are typical digital sensor protocols, and so the sensor is transporting data by these standards. And there's a huge variety of it. You see, I made 3 dots here on purpose. There are so many that are new that might be just for specific applications. So digital sensors are really everywhere. An example of why, even though we call all of these sensors digital, digital is not equal digital. I just picked an example here. I picked 3 standard consumer MEMS accelerometers here from STMicro, Bosch, and Analog Devices, and just want to show you how different these devices represent their data. Not only that the power supply varies, they have different resolution of their measurement values, and that, having said that, they also are able to transport their digital data with totally different transfer speeds. And once you have the electrical and logical interface ready, then you need to know where in the memory of the device your measurement value is stored. So you see, every device has a total different way of representing the data, even though all of these data is represented digital. And that is important for someone who has to work and test, work with and test MEMS digital sensors, because the variety is huge. I give another quick view on how data is then interpreted once it actually is delivered by the sensor. So here you see a typical consumer accelerometer with a quite wide range of quite a sensitivity range. But the SPI data output that is captured has, of course, a decimal representation, and that correlates to the measured acceleration of that sensor on that specific axis. So you see, it's not only getting the sensor connected with the right electrical interface, with the right protocol bus, but also be able to properly interpret every sensor's output in the right way. To use it in an application is quite challenging due to the variety that is possible. So then there's another aspect that comes into the game when we talk about digital MEMS sensors. The complexity of systems has increased because MEMS sensors are simple in a way, easy to handle, they are cheap, but this introduces quite some market dilemma for companies that manufacture and for companies that want to verify the sensor's operation. The average selling price of sensors has to go down. Remember what I said earlier about the number of sensors that are equipped in an autonomous car. It requires, the industry simply requires vendors to go very low in average selling price, and that actually contradicts the requirements that are caused by the complexity that is constantly growing as more and more functions go into these sensors. And to cope with that, you need to have a flexible test system, because you have a cheap device and you don't want to add significant extra test cost, even though testing a sensor is quite complex. So that is a dilemma. Then another few words about why testing. I mean, we all could simply say, okay, we rely on the sensor vendor and simply rely on the data sheet and simply say, okay, this sensor is doing what the data sheet says. I can use it in my application. I picked here 3 relatively prominent examples for MEMS sensor deficiencies and attacks, actually. The first one here is a drone attack. The drones were attacked by very intentionally created acoustic noise, but with that, it was possible to basically create influence on the accelerometers inside these drones, and so they were able to crash drones. The same was pretty much done with other autonomous, in that case, toys like RC cars, or simple applications like fitness trackers. They all were quite sensitive to acoustic injection attacks. And the most recent one that is relatively new is actually an attack to voice-controlled systems. In that example here, Google Home, Home Alexa, some of you have these devices at home, where a modulated light signal was able to inject acoustic wave messages to the microphones in that device. And why I show these three examples is the purpose is to ensure very early in the design and also in the integration phase, when you integrate MEMS sensors into your products, you want to be very sure that you have not any deficiencies in that device that could harm basically either people or even make your product not really attractive in the market. Okay, when we talk about testing, I need to create a little bit knowledge about what we call system level testing. If you're not in the MEMS sensor, let's say manufacturing business, then you might not know MEMS sensors are these days packed with several dies. So it's not longer a single sensor element, it's really complex systems in these sensors. And as sensors become more and more, let's say, capable in terms of machine learning algorithms, these sensor packages that are still very small contain lots of hardware. So that means when you test such a system, the full operation of the sensor can only be tested when you have a fully packaged part, and that is what we call final test. So we don't do wafer test here, we really test the final system. And what S-test really is a system level test solution.